Alright folks, so in this video we're going to look at loop invariant, and this is the second part of the series on loop invariant. And so first recommendation is that you must watch at least the first video to understand a working definition of what a loop invariant is. You must get that idea before you start exploring some of the problems that I plan to introduce in this video and in subsequent videos that use loop invariant. So assuming that you've already watched the first video on loop invariant, I'm going to, in this video, look at the factorial problem. We're going to look at the factorial problem, and the way the factorial problem is defined is, let's say if I want to calculate what 5 factorial is. So 5 factorial is something which is defined as 5 times 4 times 3 times 2 times 1 times 0 factorial, where 0 factorial is actually equal to 1. Okay, so instead of looking at a recursive solution, we're going to look at something that is a non-recursive solution, something that is an iterative solution. And by using an iterative solution, I'm going to introduce a loop at some point. And in order to construct a loop, in order to construct at least a correct loop, right, rather than using a trial and a catch, using kind of a trial approach where I'm still not sure what my Boolean condition in the loop is. Will my loop dominate? And I'm just going to use something called a loop invariant, which will at least allow me to come up with a correct solution in the very first try here. So let's do this. Let's at least start giving the signature to this method. So the method over here is to calculate the factorial. So I'm going to start off by saying in Python def let's say factorial. Let's just call this factorial. Okay, I want to compute a method which is factorial of n. Okay, and at some point I'm going to formulate my solution right here in let's just use the color blue for all the Python code that I'm going to write in this space. Now, before I even start thinking about the code base here, let's just do this. Let's just make things a little bit simple. Let's just say m equals to n at some point. Okay. So I'm just introducing a new local variable, and this new local variable is m here, and I'm just going to, in the base start, I'm just going to make m equals to n. Okay. Now, is there a loop invariant? Is there a loop invariant I can construct at this point that would at least allow me to formulate my loop correctly? So let's do this mathematically. What I'm proposing here is mathematically what I know is that this n factorial that I'm trying to compute, whatever this n factorial that I'm trying to compute here is going to be equal to whatever is m factorial times the result. Let's just think about this for a while. Okay, first thing, this result. Okay, let's actually do this. Okay, let's get rid of this add here. Okay, so let's think about this for a second. This local variable, or at least this variable result here in my loop invariant. So this entire thing over here, first thing is my loop invariant. This is my loop invariant. Okay, so this is my loop invariant. And what I'm saying here is that this result is something that is going to compute, is going to contain the actual result of whatever n factorial is going to be after this method terminates. Meaning that as I complete my code here, at some point the very last line is going to be return result. Okay, and you have guessed here that this method is supposed to return back a factorial of n. That n factorial, whatever that number of n factorial is going to be collected in result, and then eventually this method is going to return back whatever that result is back to whoever called factorial in the first place. Okay, so if this is the loop invariant here, which must be consistent, something that must be valid at very specific points in my code. Okay, so what are the specific points that this thing must actually, the loop invariant must actually hold? These specific points, at least from the first video, what you've learned here is this is something that must hold. It must hold just before the loop begins. So let's do that. Let's create a loop here. Okay, so at some point I'm going to have a loop. So let's just say while. Okay, and let's just put these ellipses for a time being. Okay, and so my loop is something that begins on this line. Just before this line, okay, let's just say just before that line, meaning, let me just use a slightly different color. Just before that line, meaning right here, is something that my loop invariant must hold. Let's create this point as point 1. Point 1 is that first place that the loop invariant must hold. Just after the while loop, meaning just before the body of the while loop executes. Okay, let's create a placeholder for the body of my while loop. So let's put everything in orange here. I'm just creating an indentation just to be clear that this is the body of my while loop. Just before the body of this while loop executes, I'm going to create a placeholder. Let's create this placeholder as 2. 2 is another point where my loop invariant must hold. Okay, and I'm going to create a third point which is right here just after the body of the loop. It's just another placeholder that this loop invariant which I've just proposed here, which is n factorial is equal to m factorial times result, must also hold at this point just after the body of the loop here. Okay, okay, so let's just ensure that it is actually valid at this first point here. Okay, so if n factorial equals to m factorial times result here, let's just play with some numbers. Let's say the user passes n as 3. Let's say n is actually equal to 3. If n is 3, I know that n factorial is basically 3 factorial equals to, what is m factorial? If m equals to n, m is going to be 3, meaning this is going to be 3 factorial. What should I multiply 3 factorial with? What should this box be so that 3 factorial times whatever this value is in this orange box is going to be equal to 3 factorial. This box in orange, meaning your result, should actually be equal to 1. Okay, so what I know at this point is that just before the loop begins, I must declare my result. I must declare my result actually being equal to 1. So if I make my result equal to 1, and let me be consistent with my colors here. So let's say result equals to 1. If m equals to n and if result equals to 1, at this point 1, just before the loop begins, my loop invariant actually is valid. It's actually valid because if I take result equals to 1 and I multiply that with whatever m is, meaning m factorial, is going to be equal to n factorial. This is excellent. So I know that my loop invariant actually holds at that point. So let's just put a checkbox there. This thing actually holds at point 1. Does it hold at point 2 now? Okay, what are the values of m, n, and result at point 2? Well, m, n, and result haven't even changed. M, n, and result are exactly what it was earlier at point 1, so I know that it also holds at point 2. Okay, now, sure, if I were to continue the same lines of reasoning, I know that if nothing were to happen in the body of my loop, it also is consistent at 3, right? It's also true at 3, but I need to ensure that my loop terminates at some point. My loop must come to a termination. As my loop is going to come to a termination, what I need to do now is I need to start thinking about what is it that needs to go into the body of the loop, and what is it that needs to go into the Boolean expression that would be the termination condition of my loop here. Okay, so let's do this. Given this loop invariant here, okay, which must hold at 1, 2, and 3, and in order for my loop to converge to some termination, what I'm saying here is that this local variable m that I've just declared here, so this m should be something that should be greater than 0. Okay, so my condition is m should be greater than 0, and the body of my loop, the very last statement of the body of this loop, I'm just going to say m minus minus. Okay, m minus minus in the last statement of the body of my loop, and the termination condition m being greater than 0. This at least ensures that my loop comes to some termination, because m is something that keeps on getting decremented in the body of the loop, and at some point it's going to be equal to 0, at which point my loop terminates. Okay, but I still need to ensure that as this loop keeps on running, I must ensure that at point 2 and at point 3, the loop invariant always holds. This thing should always hold. So let's do this. I'm just going to say at this point 2, okay, let's just create some placeholders. Using those placeholders, what I'm going to do now is I'm just going to say that at 2, n doesn't change. N is going to be constant. So I know that's going to be n factorial. N factorial equals to whatever is the value of m at that point. Let's just make it m. Let's just use m2, m subscript 2 factorial. Whatever is the value of m at that point there, okay, times result times result 2, whatever was result subscript 2. Okay, I'm just creating whatever's result at that point. Let's just use result subscript 2, whatever is the value result at this point 2. Whatever this is, what would the loop invariant be at point 3 then? At point 3, the loop invariant is going to be, well, n doesn't change, so n is still going to be n factorial. Okay, whatever is m at that point, let's call it m3 factorial, times whatever is result at that point. Result is going to be result subscript 3. But I know that whatever this m is at this point, well, m has just been decremented by 1. If m has just been decremented by 1, then m at this point could be rewritten. This entire thing could be just be rewritten, and just to make it simple, is going to be n factorial. Let's do it this way. It's going to be just be equal to m subscript 2 minus 1 factorial, because m has just decremented by 1. Okay, so m3 can be rewritten as m2 minus 1 factorial times result subscript 3. If this entire piece in orange is equal to n factorial, I also know that this entire piece in pink is also equal to n factorial. If this piece in orange and this piece in pink are equal to each other, I can rewrite this as m subscript 2 factorial times result subscript 2 equals to m subscript 2 minus 1 factorial times result subscript 3. Okay, now could I do some more simplifications here? Okay, I can say at this point that whatever this m2 factorial is nothing but equal to m2 minus 1. I'm just going to rewrite the first piece here, m2 minus 1 factorial times m subscript 2 times result subscript 2 equals to m2 minus 1, whatever is on the right hand side, which is this piece over here, m2 minus 1 m subscript 2 minus 1 factorial times result subscript 3. Okay, why did I do this? I did this because now I know exactly that this result subscript 2, whatever this result subscript 2 is, can, or let me do this way, this result subscript 3, is actually equal to whatever is m2 times result 2. Okay, I can rewrite this result 3. Whatever is result that must be at that point is nothing but equal to m subscript 2 times result subscript 2, meaning that I can now put one more statement in the body of my loop. Okay, is that result, the way result changes is result equals to result times m. Okay, whatever this result is nothing but result times m. Result equals to result times m. Okay, so, and there you go. I've just finished the whole factorial of my. I've just finished the complete factorial problem using loop invariant. I just made sure the loop invariant holds, and by ensuring the loop invariant holds, I've at least written this piece of the code. Let's check this. Let's just check this that actually is valid. Okay, so what I'm going to do now is I'm just going to create few columns here. Let's create a column 1, okay, which is going to be the values that are actually at this point, just at that one place 1. In fact, let me do this on the next video, just so that we I don't want to keep my videos too long. I'm just going to keep it intentionally short. So let's just stop this over here and let's do the next video continuing at this point to ensure whether my loop invariant really holds at 1, 2, and